Hi, I'm Vyshnav Mohan and I'm a PhD student at the University of Iceland. Today I'm excited to share my ongoing research with Laurus Thorlasius at the University of Iceland and Frederick Otterson at the University of Southampton. So let's begin with the two-point functions of operators acting on a thermophile double state. At late times, these functions oscillate erratically around a constant. However, something peculiar happens when we take a coarse-grained semi-classical limit. These functions exhibit indefinite exponential decay. And it turns out that this exponential decay is intimately tied to the existence of black holes and black hole horizons in the bulk description. So understanding the restoration of information both in the boundary theory and in the bulk forms the premise of my work. A natural question to ask here is, where did we go wrong? To trace the loss of information, we have to look at another important aspect of black holes, their chaotic dynamics. Chaotic systems display level repulsion. However, when we coarse-grain the energy levels of the CFT, we lose this crucial information. And it turns out that there's a natural way to fix this, and that is to introduce an emergent random matrix behavior. And in particular, we can add a term called signed kernel to the two-point function calculation, and the resulting corrected two-point functions saturate at late times. To make the saturation quantitative, we can expand the corrected two-point functions in powers of the boundary anchoring time, and we get the following series. Now, can we reproduce this from a bulk calculation? In the bulk, it turns out that we can calculate the correlation functions using a geodesic approximation. We'll capture the dynamics of the geodesic by treating it as a particle whose action is determined by its length. Quantizing the system lets us compute the boundary-to-boundary propagator. In the semi-classical limit, this reduces to a saddle point approximation. When we include the classical saddle points, the semi-classical propagator decays exponentially. However, when we include certain configurations called constrained instantons, we get a different behavior. The constrained instanton configurations are built out of tunneling solutions. Here we have displayed a one instanton configuration where a single tunneling trajectory is attached to a classical scattering geodesic. We can think of the tunneling part of the configuration as a baby universe emission. We can also have multi-instanton configurations where multiple tunneling trajectories are attached to classical scattering geodesics. And we find that when we sum up the contribution of all of these multi-instanton configurations, we end up with the same boundary series that we obtained earlier. In conclusion, what we have shown is that the inclusion of these constrained instanton configurations in the bulk can present a path towards the saturation of the two-point functions in the boundary theory. Thank you.